Gaussian elimination is a technique that's used to solve for multiple unknowns. For example, we had three equations and three unknowns here. It's a technique where you could actually quickly solve for x1, x2, and x3. We first start out with a coefficient array. So I'm going to write out the coefficients. I'm developing something called an augmented matrix where I have my coefficient array, A, on the left here, and then I'm augmenting it with the resultant vector. So a lot of times I may or may not have this vertical bar in here. So that's our augmented matrix. And for example, that first line just corresponds to x1 plus 2x2 plus x3 equal to 0. Ultimately, what we're trying to do is transform this original array into the form 1, 0, 0, 0, 1, 0, 0, 0, 1, and the augmented array, we're going to carry along with that a transformed b. If this is our original b vector, we're going to have some sort of augmented b, and I'll write that as with a prime. This top line is 1x1 plus 0x2 plus 0x3 equal to whatever that b1 prime is. Obviously, these two cancel out because we have 0 coefficients, and we can just say now that x1 equals b1 prime, x2 equals b2 prime, and x3 equals b3 prime. We're trying to solve these system of three equations for those three unknowns. The first step is to normalize position 1, 1. It's already a 1, but if we had had something like a 2, 4, 6, the first step would have been to make this position, the 1, 1 position, a 1. Again, once we have it in a 1 in the 1, 1 position, the first step is to make a transformation. And we're going to work with the second row. The first row is fine. New row 2 is going to be equal to the old row 2 minus whatever coefficient is directly below that 1, that's a 4, times row 1. If I rewrote this, we always do the same transformation with our b. Again, keep in mind that these are just algebraic equations. So if you manipulate the left-hand side of an algebraic equation, you have to manipulate the right-hand side. And we're going to subtract, so I'm going to write just a negative sign here in parentheses, indicating that we're going to subtract 4 times row 1. 4 minus 4 is equal to 0. And this right here is the main reason we're doing this transformation, because what we've done now is we've eliminated an x1 term from the second equation. So this is our new row 2. The reason I did this now is I've eliminated x1 from this second row, and I'm moving in the direction of making my augmented matrix in this form. The next step is to define a new row 3 is equal to the old row 3 minus, in this case, I'm going to put a 7 because I have a 7 here that we're trying to get rid of. We're trying to get that 7 down to a 0. So I have to subtract 7 times row 1. So this is our new row 3. Now put together our augmented array at this point. This left-hand column is exactly what we want. So that's what we want. The next step is to get this minus 3 to a 1. So you divide new row 2 is going to be equal to the old row 2 divided by that minus 3. So this is our new row 2. I'm going to rewrite our augmented matrix. So now you see that we have these in the form we want, and this is in the form that we want. The next step is getting this minus 6 that's below our 1 to a 0. So similar to what we did above, we say the new row 3 is equal to the old row 3 minus negative 6 times row, and we're not doing row 1 this time, we're doing row 2, because row 2 has that 1 in that 2, 2 position. Negative 6 minus negative 6 is 0, and that's why we're doing this transformation, because now we've converted that x2 coefficient in the third equation to 0. This is our new row 3. If I write this in terms of x's, we see that this is in the form the negative x3 equals negative 3. So obviously x3 equals 3. And the next step is to normalize this 3 to a 1, and that's easy. We just divide everything by negative 1. That is normalizing that 3 pivot is what it's called. This is called a 3 pivot. This is a 2 pivot, and this is the 1 pivot. If you look at it now, this whole part, the lower left part here, is all in the form that we want. The process now is to convert this 2 into a 0. This begins the back substitution. It's called back substitution because now we're going back up in row. New row 2 is equal to old row 2. We're going to subtract 2 times the third row. So that's our new row 2. So now my augmented matrix becomes, this is starting to look like the form we want. The only thing now we need to do is eliminate the 3 and the 2. So we're going to have a new row 1 is going to be equal to the old row 1 minus 3 times row 3. Again, we did this so that we can eliminate that 3. So now we are almost there. Our augmented matrix at this point, the only thing we have left is to get this to a 0, subtract 2 times row 2 because we have a 1 there. So the new row 1 equals old row 1 minus 2 times row 2, because row 2 contains that 1. That's our new row 1. Final matrix array then is 1, 0, 0, 11 thirds. Row 2 is 0, 1, 0, negative 19 thirds, 0, 0, 1, 3. What this is telling us is that x1 is equal to 11 thirds, which is equal to 3.67, telling us that x2 is equal to negative 19 thirds, which is equal to negative 6.33, and x3 is equal to 3. Let's see if that's the same as what we got in Excel. We have 3.7 for x1, we have minus 6.33, and we have x equals 3. So this is how people used to solve simultaneous equations. I mean, you can use algebra, and the first programs to solve simultaneous equations actually used exactly what I went over, and this is known as Gaussian elimination.